To summarize the main differences between a voltaic and an electrolytic cell, we'll post the main points as they relate to the Daniell cell in a table. As previously mentioned, the voltaic cell generates electrical energy from mechanical energy. The electrolytic cell is the opposite. The cathode is positively charged in the voltaic cell and negative in the electrolytic cell. To limit repetition, I didn't write it, but you could also add, if you wish, that the anode in the voltaic cell is negatively charged and the electrolytic cell, the anode, is positively charged. The oxidation half reactions at the anodes show electrons being lost from zinc in the voltaic cell and copper in the electrolytic cell. Likewise, the reduction half reactions at the cathode, copper ions to copper metal in the voltaic cell and zinc ions to zinc metal in the electrolytic cell. The net ionic equation for the voltaic cell is the reverse equation in the electrolytic cell. Most importantly, the voltaic cell's redox reaction is spontaneous, while the electrolytic cell is non-spontaneous. That is, electrical energy is required to drive the reaction. So how much electrical energy are we talking about here? The standard cell potential for the voltaic Daniell cell is positive 1.10 volts. For the electrolytic Daniell cell, the standard cell potential becomes a negative value, indicating that the reaction is non-spontaneous. While the positive value means that this is the amount of electrical energy produced by the reaction, the negative value means that this is the minimum amount of electrical energy required for this reaction. When you look at your data booklet showing the table of selected standard electrode potentials, you can fairly accurately predict spontaneous redox reactions as they would occur in a voltaic cell. The strongest oxidizing agent reacting with the strongest reducing agent, and as long as the standard cell potential has a positive voltage, any combination is theoretically possible. And while the reverse reaction occurs in an electrolytic cell, the concept of the strongest oxidizing agent reacting with the strongest reducing agent still applies, and it is this point that caused some unpredicted results in the early years of electrochemistry. When the proper voltage is applied, 1.10 volts, zinc ions will reduce to become zinc metal, while copper metal will oxidize to become copper ions. Surely then, with the appropriate voltage, would I not be able to form aluminium metal from an aqueous solution of aluminium ions? Just a short aside here, but aluminium is the correct IUPAC word for the element Americans called aluminum. The short answer is no. British chemist Sir Humphrey Davy tried to produce chlorine gas and sodium metal from salt water using electrolysis. He got the chlorine gas, but not the sodium metal. He actually produced hydrogen gas, as you would with the copper and aluminium ion electrolytic cell. Why? Because water from the aqueous solution is a stronger oxidizing agent than the aluminium ions and would therefore react first. Recall that water can also act as a reducing agent. The electrolysis of water involves having water at the anode and water at the cathode. The products would be oxygen gas bubbling in an acidic solution and hydrogen gas bubbling in a basic solution. In this electrolytic cell, each electrode is enclosed in a glass tube to prevent the two gases from mixing. If water is to be considered as either the oxidizing agent or reducing agent in an electrolytic cell, use the standard electrical potentials as shown in your data book. I say this because your textbook talks about overpotential. In an actual lab setting, the application of the calculated standard potential difference for the electrolysis of an aqueous solution where water is being either oxidized or reduced would not be sufficient to drive the reaction. Therefore, an added potential, an overpotential, is applied to the potential difference. There are a number of reasons for this. The ions in the water half reactions and the water itself are not at standardized concentrations. In fact, water has a concentration of 55 moles per liter, while the hydrogen hydroxide ion concentrations are 1.0 times 10 to the negative 7 moles per liter. And the formation of gases at the electrodes requires additional voltage. It is not a lot of voltage, about 0.6 volts. It's important to know what overpotential is or why it's applied, but I will not ask you to consider it in your calculations. Overpotential applied to the chloralkali cell permits the chlorine ions from brine, a solution of sodium chloride, to be oxidized and have chlorine gas form at the anode, and hydrogen gas form from the reduction of water at the cathode. The products from this cell, chlorine and hydrogen gas, and sodium hydroxide, are widely used in industry. An understanding of overpotential enables more accurate predictions of electrolytic outcomes than simply using standard electrode potentials. The reduction of ions to form group 1 and 2 metals was a problem. It seemed that no amount of overpotential would overcome the reduction of water. So Humphrey Davy found that while solid sodium chloride was electrically non-conductive, molten sodium chloride ionized sufficiently to conduct electricity. The apparatus used is known in the sodium metal production industry as the Downs cell, and is shown here in a drawing from your textbook.